So good evening to everyone. This is part of a 6-day program for teachers of engineering colleges and mathematics department across the country. In these 6 lectures, we would like to convince everyone how linear algebra is useful in modern technology. We have 6 very distinguished speakers. So we start with Professor Borkar. He is from Electrical Engineering Department at IIT Bombay. Professor Borkar is of course known to all of us here, but now we have participants from across the country, from Uttarakhand and Coimbatore and Northeast and Gujarat. And so I would like to say a few words about Professor Borkar. Professor Borkar is alumnus of IIT Bombay. He graduated in 1976 from Electrical Engineering Department, but he is a mathematician in disguise and works for Electrical Engineering Department. I am from Mathematics Department, and I can say many things about his mathematics, but this is not the correct time. He got his PhD from University of California, Berkeley in 1980 after he left finished his BTech from IIT Bombay. His research interests are stochastic optimization control. He is a very well-known figure in that area, and he has written 5 books and monographs and large number of book chapters and innumerable number of very interesting research papers. He was at Indian Institute of Science for about 10 years from 89 to 99. And then he spent about 12 years in TIFR Bombay before we could attract him back to our institute about 6 years ago.
2011.
2011. Of course, he is one of the highly decorated scientists in our country. He won the Shanti Swarup Bhatnagar Award. He is a fellow of all the academies in India, whether it is engineering or science. And he is also a fellow of American Math Society, and he was elected to the fellowship of the World Academy of Sciences. All right, so Professor Borkar will talk about spectral ranking. This is a very modern application of linear algebra, and all of us use it every day, innumerable number of times, and there is no secret behind it. And Professor Borkar will explain why linear algebra is so useful in Google search or other search engines. For agreeing to come here.
Yes, I am going to talk about spectral ranking. So this is the outline. This is the poster boy of this field is Google's PageRank, which probably many of you may already know. So you will have to sort of suffer through a repetition of many things you know. And then we'll talk about spectral ranking in general, then some other example other than PageRank, and then some related matters at the end. And if there's some time left, I will also like to preach for a few minutes. I rarely get such opportunity. So I'll start with Google's PageRank. So let me just introduce what's called the random web surfer model. So this, anyway, for sake of completeness, let me just define things you probably already know. The World Wide Web, that's the sort of one, you can think of it as a directed graph. So I have drawn a directed graph here. So each node or vertex is a website, and there are these hyperlinks pointing from one to the other. Okay, and the search is typically when you search, start search, you start at some home node. Maybe this is your own website. You just go somewhere else searching, and then keep going, and eventually stop, and perhaps start a new search. So the random web surfer model thinks of this search as a random walk. So the idea is that from each node you go to one of the, so by successor I mean the nodes which come to which it points. So for this is the successor, this is a successor, this is a successor, this is a predecessor, because this is both a predecessor and a successor, and so on. So for this is a predecessor, this is a successor, and so on. So it's a directed graph. So the direction matters, and you move from each node to one of the successors with equal probability. So I will make it more formal later. And the idea of PageRank is to rank vertices according to the frequency with which they are visited. So if this everybody is, for example, clicks on comes to this site very often, then obviously it's important, and that's the intuitive idea, which makes sense. except that there are some problems in formalizing this, which I'll come to very soon. So formally, it's what's called a Markov chain in probability. So you assign probability weights to each of these nodes. So let's give them some names. Let's say 1, 2, 3, 4. So suppose I consider node 1, then look at the outgoing nodes. So this will be probability P1 to 4 of going from 1 to 4, and this is P1, 2, and so on. This will be P2, 1. So in particular, you expect that the total probability of outgoing edges add to 1. So sum over, so Pij should be between 0 and 1 because it's a probability, and summed over j Pij should be 1. Okay, so you go from I to j with with probability Pij, summed over all possible successors. It has to add to 1 because you have to go somewhere. So of course, possible that you can go from I to itself. So yeah, so the simple random walk means that all these outgoing probabilities are equal. So for each node, the number of outgoing edges is called the out degree. So for this node, there are 3 outgoing edges. So out degree is 3. For this, it's 1, and so on. For this, it's 2. So I just put Pij equal to 1 by degree. So this is the out degree of I. Okay, so you go to one of the successors with equal probability, and then you want to see which states are visited very often. But there's already a problem, namely what's called a dangling node, like this node. You don't go anywhere from, it's a dead end. So what doesn't just leave it like that. You put a self loop with probability 1. So let's say this is 6. So P66 is 1. Okay, it never gets out of there. And from Markov chain theory, you know that if there's even one dangling node, it's called an absorbing state in probability. If there's even one probability absorbing state, you will end up getting stuck in one of the absorbing states with probability 1. I mean, there's no way you can escape that. As long as there's a positive probability of hitting a absorbing state, you end up in an absorbing state in finite time and stay there forever. So then you consider the sort of frequency over infinite time of how often you visited a particular state. Only the absorbing state, if there's a single absorbing state, it will have a frequency 1 and everything else will be 0, which makes no sense. So you have to tweak this model somehow, and that's what PageRank does. So there's this alpha called Google constant, and with probability 1 minus alpha, you take a convex combination of two things. With probability 1 minus alpha, you do this. So you go to one of the successors with equal probability, and with probability alpha, you just move to some arbitrary node with equal probability. So that's basically, you can think of it as starting a new search. So as I said, you start a search somewhere, keep moving, and then end up in some. I mean, it doesn't have to be an absorbing node. You may just discontinue the search after a while, and then you start a fresh search from some arbitrary node, which is, for simplicity, one assumes is equal probability. So now the Pij is 1 minus alpha times 1 by the out degree plus alpha times 1 by the total number of nodes. Okay, so with probability 1 minus alpha, I pick one of my successors with equal probability. And with remaining probability, I just pick one node at random uniformly. And yeah, so then now suddenly things have improved. So what I have done effectively is to introduce these thick transitions from each node to every other node with probability given by 1 by n, where n is the total number of nodes. So now that makes, if I consider the matrix P formed by these probabilities, so ijth element is Pij. Now I can say that there's a path from, there's a directed path from each I to each j. In fact, there's a one hop link, so it's trivially there's a path. Okay, so you can go from, for my purposes, for what I am going to conclude, it suffices that there's some multi-hop path from each I to each j. Now it's even better, there's a single hop path. So this matrix is what's called a stochastic matrix, in the sense that all the entries are non-negative, and the row sums, each row, the elements add up to 1. So they're probability vectors. And now I have rendered it irreducible, in the sense there's a path. So there's a path from each node to each every other node. So that has an important conclusion that it has a simple eigenvalue 1. This anyway is easy to see because if I just write P times the constant vector 1, 1, etc., this is going to be 1 because they just say that the row sums are 1. This is just restatement of the fact that sum over j of Pij is 1. So it has eigenvalue 1 with the constant vector 1 as a right eigenvector. But it turns out to be a simple eigenvalue, simple positive eigenvalue, and it has the right eigenvector and it's being 1. There's a left eigenvector also, and both these eigenvectors are positive. All this is a special case of Perron-Frobenius theorem, which you have probably already seen. It's true for all irreducible non-negative matrices. There's a what's called a principal eigenvalue of Perron-Frobenius eigenvalue, which is strictly positive, and corresponding left-right eigenvectors are strictly positive. So the left eigenvector is important. So as you know, eigenvectors are unique only up to a multiplying scalar. So I will normalize it so that its sum is 1. Okay, so without loss of generality, I assume that the sum over I of pi I is 1. Then it can be interpreted as a probability vector. So pi I is probability of being in I. Then it satisfies the equation pi p equal to pi, which says that it's a left eigenvector with eigenvalue 1. Okay, these are all. Any questions about this? I am just restating the same thing again and again in different forms. So this equation pi p equal to pi translates into something interesting if you interpret it probabilistically, which is this. So if you consider this random walk xn, so probability that it is at j at time n plus 1 is the probability that it is at I at time n times the probability of going from I to j summed over all possible i's. This is common sense. Okay. So if suppose Pxn equal to I was pi I, then what that pi p equal to pi implies that if Pxn equal to I was pi I, then there's a typo here. There's an unnecessary for all I here. No, this is okay, yeah. So if Pxn equal to 1 was pi I, then pi p equal to pi would imply that Pxn plus 1 equal to j would be pi j for all I and j. So if you start with initial distribution, that at distribution of x0 as pi, so p of x0 equal to I is pi I, then the above calculation shows that p of x1 equal to I is also pi I for all I, and just by induction you can argue that Pxn equal to I is pi I for all I and for all n in fact. And so pi is called the stationary distribution of the Markov chain. So the distribution, if you just consider time n, the distribution of time n, it does not change if you start with pi. And then there's a law of large numbers for Markov chains, which says that the fraction of time you spend in state I up to time n. So that mod stands for cardinality. So number of times xm is equal to I between 1 and n divided by n. That is the fraction of times the chain was in state I asymptotically converges to pi I with probability 1. Okay. So this is I have already been talking of frequency of visits. So this pi I is precisely the frequency of visits of state I asymptotically. So then you want to rank I in according to the decreasing value of pi I. Just sort pi according to decreasing values, and whichever has the largest frequency, that's at top and so on. So this is what PageRank does. Okay, so this PageRank, there's a pun. One of the originators was a guy called Larry Page, one of the founders of Google. So it both gives him credit and it also ranks the web pages. So this is what Google search is supposed to do. You give some keywords, it will look for the sites that suggested by the keywords and rank them according to the corresponding pi. Now this is something from a book in early 2010 or something. So this could be dated. The alpha is apparently 0.85. Nobody really knows what exactly Google does. So they are not going to tell you. So it's some constant, and it kind of trade-off between. I mean, this again you take with a pinch of salt. So see, the thing is that there's a small probability with which it goes somewhere else. So if I suppose I just increase that probability, the chain would sort of go all over very much faster. So what's called, known as, see what it does is for any computational scheme, anyway, I'm going to talk about one later. Computational scheme to either random probabilistic scheme or numerical scheme to compute pi, how fast you can compute matters. Okay, so the speed of convergence will matter, and that is intimately related to alpha. The smaller the alpha, the faster the chain will mix, in the sense that it will scan the state space faster and faster. So it will speed up the convergence to stationarity. At the same time, it's further from truth, because this so it was a convex combination of it was 1 minus alpha p times alpha times, let's call it J, the uniform, the normalized matrix of all ones. It's 1 by n, all elements are identical. So this is non-informative, it does nothing, it just picks one independently at random. This is the matrix which is carrying all information. So if alpha is close to 1, then you have more influence, you give more influence to what matters and less influence to this complete arbitrary randomization. But on the other hand, it will slow down the rate at which you attain stationarity. So there's some study for a random graph by these authors, Avrechekov, Litvak and Form. They take a random walk model. Typically, they take a random graph, and typically for some of the standard random graph models, you get something called a giant component, a large connected component, some lesser nodes hanging sort of on the outskirts. And they did a lot of analytic and simulation study, and what you find is that this kind of stuff. Now, typically, suppose your search, if you go, typically a web surfer who lands up here abandons the search and goes somewhere else, then this is probably not important. But because here the outgoing probability is very small, it tends to give it unnecessary emphasis, in the sense that dangling nodes get more weight than they deserve in the PageRank if the alpha is close to 1. That's what they observed. It's not surprising in some sense. At the same time, I am not sure how much it matters, because there's a branch of optimization called ordinal optimization, which some of you might have heard of. What you try to find out is, so you want to rank several designs, and you are typically interested in, after a certain time, whether the top one will be within top 5 with probability greater than 0.9, something like that. Okay. So typically you are interested in only top ones, which is certainly true here. Suppose the Google gives you 100 top ranks, you are going to look at only first 10. And typically, even if the dangling node gets its weight jacked up a little bit, it may not make it to the first 10. So those things also matter, because this is what's called, this ordinal ranking. I will come to that later. Okay, so there are other tweaks also. This is just a more formal notation. So I have original matrix I have called p tilde, which may or may not be irreducible. And then this one is a vector of constants 1, and alpha is the Google constant. And one tweak which Google does use, it was actually started by another startup out of Stanford. Google itself came out of Stanford. This Page and Brin were graduate students there. But later on, there's another pair of students came up with something where they introduced this personalization, which gives some bias deliberately. So for example, it will put suppose I am searching for the same thing, say probability books every other day, then it will put some higher probability to things closer to me, my neighborhood and so on, and thereby improve the performance. The naive scheme is agnostic, it just doesn't look at who's surfing. But this tends to give some weight to the person who's surfing, what he looks for and so on, and even those things can be tweaked further. So this is called personalization. This is one tweak which has been done already. This is perhaps the only significant theorem I'll point out. So it says that if the eigenvalues of p tilde are 1, I have sorted them in decreasing order, then the eigenvalues of p are just everything else gets multiplied by this alpha. So in particular, typically this is not irreducible, and the original p tilde is not irreducible, and typically it's also doesn't have a single communicating class, in the sense that there will be several. So there will be several kind of regions where there's a path from each node to each other node, but there may be paths, say, some other nodes outside from where there are paths here. And those who know Markov chain theory will know this. I mean, so these are the regions where there's a path from each node to each other node, but once you are inside, you cannot get out. Whereas from other these nodes left outside, you can enter one of them. So eventually, you will enter one of them. Basically, that's what happens. So these are Markov chain theory. These are called transient states. This can be depending on if it's infinite. If they're finite, they have to be recurrent, but otherwise they can also be transient. But anyway, the thing is that if it's like this, if there are more than one such class, then the eigenvalue 1 has a multiplicity bigger than 1. So the lambda 2 will also be, or sorry, lambda 1 will also be 1. And then the spectral gap, the after this tweak, is 1 minus alpha, because the second, that's what you get. So the which tells you from either linear algebra or Markov chain theory that the iterates of p to the n. So the eigenvalues can be multiple and complex, etc. If I ignore that, let's assume you are in a simple situation, then you can write this left eigenvector, right eigenvector transpose. Okay, so this kind of decomposition you have. So if I can take the first one out, that is, no, sorry, yeah, this is correct. So I have, so this is the one eigenvalue is 1, so I have that vector of 1 times pi. Pi I had already written as a row, I think, if I recall. And then I greater than equal to 1. So I have started counting from 0. So 0th is the 1. I will have some. And if I keep taking powers, this doesn't change, because power of nth power of 1 is 1. So these will start going down to 0. Okay, and so you get in the limit matrix all of whose rows are pi. That's what it says. But this tells you the rate of convergence. The slowest one will dominate the rate of convergence, and that will be essentially, that's what you get. Yeah, there won't be. It's just the alpha which so lambda 1 is 1. Yeah. So others will be the slowest one dominates.
Like there is no dependency seen on the right of lambda k.
Yeah, it won't. I mean, it will be a lesser, lower order effect.
I suppose you are trying to capture what is the speed of.
Yeah, speed of convergence. So it will be sum of exponentials, weighted sum of exponentials. The slowest decaying exponential matters.
No, I understand that,
yeah.
But I don't see that dependency on that on the right hand. I understand it depends upon the lambda. If the lambda is close to.
Yeah, so no, basically I'm just so there are some different lambdas. So I am dominating this by some constant times the slowest one.
That is where the k comes.
Yeah.
K is kind of bounding the lambda.
Yeah. Lambda 1 raised to n. This another thing which this Google tweak does is that this equation pi p equal to pi reduces to something simple because of the particular structure. If I write it in terms of p tilde, it's exactly that. And then it's even better because that 1 minus alpha p tilde t is kind of it's a nicer object. Its eigenvalue is, the top eigenvalue is 1 minus alpha. And I can iterate the linear system, it has this explicit solution. So that's basically all algorithms are based on that. And yeah, so we are essentially trying to solve that linear system on top, but it reduces to this for Google. And this iteration, which is basically a stable linear system, will converge exponentially for free, which sounds nice, but it's not that nice because the size is incredibly large. So this is where most of the work is. Okay, that's one problem. Another problem is that the graph keeps changing, and the graph itself changes, and the weights also, the sort of the edges also, the number of nodes itself changes. Even if that was fixed, it would be something, but that itself changes, and the edges also keep changing. So what typically, so you need sophisticated numerical techniques, and most of the work in this area is on that. I mean, it's just solving a linear system, but it's no longer simple. So what typically is done is to keep updating using if the graph doesn't change too much. Of course, it doesn't change overnight to something drastically. So you keep doing local tweaks to keep up, keep tracking the solution, and then every now and then you redo the whole thing from scratch. Which is why this is kind of Google has this server farms and so on. So, and among one of the spin-offs is that they have to cool them. So Google also funds energy research, alternative energy, and so on. Yeah, because this error accumulates. I mean, you are doing local. You are trying to track something randomly changing graph, and which are again you don't want to do anything very complicated. So typically some local tweaks, and slowly it starts. The error starts adding up. So every now and then they'll redo the whole thing. Yeah.
You can't plug in the dynamic graph into the system. It doesn't work like that.
No, but it's a very large graph. So, in fact, see, there are other. I don't know what Google does. What I just told you is I know one French search engine does that, because I have some friend who consults for them. But I suppose Google must be doing something similar, that have some kind of tracking of slowly varying. But I mean, even if you are tracking a slowly varying signal, eventually the errors can accumulate. So.
Can you compute changes in your PageRank rather than computing the PageRank itself?
No, that's what they do. So on a daily basis, that's what they do. But that's not enough, because eventually things will pile up and it will be totally off. So they redo the whole thing every once in a while. So this was just a sort of trailer. So this is a special case of what's called spectral ranking, which is what I want to talk about. So the abstract framework is that I suppose, again think of a graph. Suppose I want draw the influence Wij from his acquaintance or whatever j. Then what is this net influence? You would think just sum up over the influence of you get from your neighbors, and sum over j or Wij, but that's not quite right, because your acquaintances may be kind of non-entities. So you know a million non-entities, still doesn't gain you much. So I put this thing of Kevin Bacon, because that guy appears in a different context, small world networks. So he was some kind of secondary actor who did bit roles in many films. So there's this famous graph where you draw, if two actors have been in the same movie, you draw a link, and this guy tops the list because he acted with everybody. So it's like Erdos number, you in Hollywood, you have Kevin Bacon number. Also Erdos number means something, because Erdos was a great man, but this guy was not. But nevertheless, so just want to emphasize the fact that just a naive ranking may not tell you much. So it should be some you also take a weighted average of the weight of your friends, I mean the status of your friends. So that suggests x equal to wy. But then y will be wz, because y themselves, each y will have their own friends. So you have to look at xn plus 1 equal to wxn, keep iterating till you reach infinity, but then you may not reach infinity, it can blow up. It depends on the matrix W, depending on the eigenvalues, the spectrum, it can decay to 0, blow up, or just do something else. But so what one does is to normalize it. So, and the normalization is irrelevant, because as I said, it's ordinal comparison. You only care who's higher than whom. It don't care how much. So if my weight is 10 and yours is 5, say, and that's one possibility. Another is mine is 100 and yours is 50. The numbers mean nothing. So the scaling is irrelevant. So you keep normalizing, and this is a known algorithm. And we'll come to that. So if W is irreducible and the graph is not periodic, then you, for almost all initial conditions, you will converge to the correct Perron-Frobenius eigenvector, which is strictly positive component wise, and the normalizing factor will convert. It should have been normal AXN. I think that A is missing. Normalizing factor will converge to the Perron-Frobenius eigenvalue. Okay, and almost all, because if you start with some eigenvector corresponding to one of the other eigenvalues, you are never going to get out of that. But if you consider the principal eigenvector and consider the subspace spanned by all other eigenvectors, that's a lower dimensional subspace, so it has 0 volume. So if you take a random initial condition with probability 1, you are going to avoid that. So, this is called the power iteration, and there are other normalizations possible. I think I have missed A everywhere. This should have been norm of AXN. So, then the spectral ranking just tells you that you rank according to you sort EI in decreasing order and rank accordingly. And as I said, it's ordinal comparison, so the normalization does not matter. There's another variant where by a guy called Cart, there was a social scientist. He put some damping factor and beta, which is between 0 and 1. So it's a nice summable thing. You don't have to normalize, and you actually get that I minus beta W inverse, and then rank according to this. He was actually, his idea was to estimate prestige. I don't know how you would do that, but anyway, this is some historic work. I mean, not very recent. He was one of the early people to work in along these lines to come up with some idea of how to sort of quantify prestige. And this kind of theme has become common in particularly social networks research, where it's called eigenvector centrality. There are various special cases which I will come to soon. Okay, so these examples are precisely that. So this is an important one. This is a Kleinberg's hit scheme. So you take the adjacency matrix of the graph with the vertex set V and edge set E. So adjacency matrix means Aij is 1 if Ij there's an edge Ij, and 0 if there's no edge. And then let H and A denote the principal eigenvalues of A transpose and A transpose A. Okay, so these are symmetric matrices. And you do this, they can be computed by alternating power iterations. So you, I mean, it's just a tweak on power iteration. You multiply by A transpose and then by A, then by A transpose again, and so on. So you will get from the odd x2n converging to, or rather the xn's converging to something and yn's converging to something else. So they give that these two vectors, and they have different interpretations. They are called hub and authority rankings. So the intuition, the authority is the ranking according to top eigenvector A transpose A. That has this intuition. Anyway, these terms Kleinberg himself coined. That everybody kind of points towards, their paths tend to point towards them, and hub is the kind of the path. Lot of path. Other nodes are reachable from them. So paths, outgoing paths. So it's kind of directionality in this. It was originally used for a certain search engine, which was not very successful, because for one thing it was very susceptible to spamming. But it's now very popular in social networks, and this itself leads to interesting things. For example, if I want to find, for example, one of the industries which supports this kind of work is advertising. You want to influence some 5 people, convince them to advocate your cause. Okay, how would you find them? If you take the top 5, that often doesn't work. So this actually we experienced in some work I was doing long back. So that was a little different, but the same flavor. So you suppose I come up with a ranking according to something and take the top 5. That's one choice. Another one is take the top 1, remove him from the network, find the top 1 of what's left, and so on. Then remove him, find it. You get different answers, and it's believable why. For example, there are 2 people who are very close to each other. There's, say, 2 friends, they were both very influential. Okay. Putting both of them in my basket is not going to help much, because if one of them is canvassing for me, the other more or less will. I mean, it's not going to add. Most of the people they reach out to are going to be common. So it's better to remove him and then look again for who's him. In fact, this guy may be drawing his influence from his proximity to this guy. So remove him, look for again who's the best in what's left. It may be somewhere else. So all kinds of non-trivial issues. I mean, problems are messy, and they're combinatorial typically. They don't have clean answers most of the time. This, in fact, this is not linear algebra result, but the most successful heuristic has been something due to Nimhauser, Fisher, and Wolsey, which again Kleinberg was the first one to use it, and it has been used often, which is this for this. You show things like submodularity, etc., and then show that greedy is 1 minus 1 by E optimal, and use greedy scheme. So this is some people came up with the scheme for ranking journals and authors. So I have given only the authors version, the similar thing for journals. So you are looking at a large number of publications, take 1 by the number of publications by 1 plus co-authors or number of co-authors of I times 1 by 1 plus number of co-authors of J. This is just to avoid division by 0. That gives you some number. You normalize it, call it Pij, and do Google kind of thing, and rank according to the stationary distribution of this. Incidentally, earlier I had one line which I forgot to talk about when I was talking of Google. There's something called link farming. You can jack up your own rating by manipulating. For example, you can farm. I mean, here you can form cartels and refer to each other and so on. And there are companies which are offering you the service of jacking up your Google rating by you just buy their product and do some hera-fairy and jack up your rating. So this another issue one has to worry about. So I'm making. I mean, if you just look at the linear algebra, it's simple, but if you go deeper into it, it's a mess.
Who is offering the service for?
No, I don't remember now. Huh?
For professors, who is offering the service?
Oh, professors. I don't know. It's a good, actually, business proposition. One could start something. So it's another one for P2P networks, as peer-to-peer networks, where you share files, etc. So this PJ is some prior trust in J. This is again to avoid division by to get rid of division by 0. I'll come to that soon. So each transaction, after each transaction, I rates J as +1 or -1, say. Okay, and then Sij is the summed over all transactions, so it can go negative also. And then Cij is basically the maximum of the positive part of Sij and normalized if the denominator is positive. So if it's always negative, then you just plug in Pj. So Pj is just to take care of situations where you would end up dividing by 0, and then rank according to the stationary distribution by Cij. These are in fact the same people. There's Haveli Wala and Kamwar. They said there's two Stanford guys who started this personalized web rank. Same people came up with this. So I started a company for the personalized web rank, which of course this Brin and Page bought up. So they end up working with Google. Yeah, this is a more recent. It's interesting, and some of you may anyway eventually give the references. And this author is particularly well known in IIT Bombay. He's a former gold medalist, guy called Devrat Shah. He and his collaborators came up with this. So there's some old model called Bradley-Terry-Luce model. The game theorists would have heard the name Luce. This is Luce and Raifa book on game theory. So the idea is that you assume that people prefer product I over J with probability Wi by Wi plus Wj, where some Wi is some unknown weight which is a priori there and which you don't know. And then you want to rank according to this decreasing Wi's or normalized version of that. Mu I is Wi by sigma Jw. So you want to, what you have is some empirical estimate of Pij. Suppose you have several people choose between I and J. So this Uij, empirical estimate of Pij, could be just the number of people who preferred I over J divided by total number of people who compared I and J, something like that. So something simple like that. So Uij is your estimate of Pij, and Dm is the maximum degree of vertex. And what you do is define this matrix Q. Qij is Uij by Dm maximum degree, and 1 minus blah blah whatever remaining probability, you just put a self loop. Pi is a stationary distribution, and you rank, it's called rank centrality, and then you rank according to that, use pi as a surrogate for mu, and they have a precise error bound. Yes, actually I have simplified it. There are more terms also, suppressed some of the things, but just kept the dependence on the number of nodes, which is logarithmic, and the number of samples per pair if they are constant. Okay. And there are some extensions. This is maybe slightly going off the tangent, but let's see. So here at first I talk about the continuous version. Suppose I rewrite, make an incremental power method. So instead of writing xk plus 1 is axk by norm axk, I take a convex combination of previous step and just make a small change, 1 minus gamma xk plus gamma axk or norm xk, and rewrite it in that form. And suppose I let gamma go to 0, I will get a differential equation. So here I have written some differential equation from a different origin altogether, and so there you would get x naught equal to ax by norm x minus x. Here, if this is the differential equation which these two people came up with. If I pull this term out, then it starts looking like somewhat like the normalization is not exactly norm, but something like a continuous version of power method with a different normalization. Now, this term, if you have a differential equation, if I put some arbitrary positive function in front of it, positive number say, if I put some alpha t and alpha is bounded away from 0, it does not change the trajectory, it only changes the speed with which you move along the trajectory. So, for the qualitative purposes, it's the same differential equation. Okay. So, if I pretend that this is positive and bounded away from 0, it would be sort of like a continuous version of power method. Now, this they came up with they're studying something called autocatalytic networks, which are proposed as origins model for origin of life, in the sense that you have several chemical reactions. So, you know what catalysis is. Suppose the reaction A catalyzes reaction B, B catalyzes C, C catalyzes D, and D catalyzes A again. Then if they start, they will self-sustain, they will go on forever. So that is supposed to be one possible way life could have started, in what they call primordial soup of proteins and so on, due to some whatever cataclysmic event like lightning or whatever, or earthquake or so on. Suddenly some autocatalytic reaction started and sustained. So, this is a famous model by two chemists, Eigen and Schuster. And these people have analyzed both theoretically and by simulation variations of that, and with many interesting conclusions. And this is the equation they do, which sort of like, for their purposes it works. But the one catch here is that I said that this kind of leap of faith to say that this will always be positive, etc. You have to ensure that there's a better model which does that for free, which will better in the sense for the different context, but as a continuous power iteration method, it's better because the positivity comes for free. So, I'll come to that soon. Before that, there's another algorithm. It's called multiplicative weights. This is another very popular algorithm in computer science. So, what you do is that you have to choose between several decisions, several alternatives, and start with equal weight for all of them. And then at time t, you basically pick one of them with probability proportional to its weight. Okay, and you keep updating the weights, and you get some cost or reward, whatever, of the decision. Let's call it M1 to MNT, which are, for simplicity, I put them in -1 to 1, and then you sort of update the weight according to that. So, there's various tweaks. I have said costly decisions. You might consider only the ones with positive cost, or you can consider either positive or negative. Both possibilities exist. But basically, you just tune, modulate the weights depending on the rewards you are getting. So, this is like a power method with random matrices. And this has been analyzed with, and it's been promoted in a big way by a famous man called Sanjeev Arora. This is just one of the major tools, and I'll tell you where it. Anyway, I'll give the reference later. There's a long paper by Arora, Hazan, and Kale, which talks a lot about this. And they have given in sort of finite time analysis and so on. So, one good thing about computer science papers is that they are not happy with asymptotic convergence. They'll tell you what happens in finite time, because they know, as one economist said, in the long time we are all dead. So, we have to, algorithms need to do something before that happens. So, the continuous analog turns out to be what another famous equation called replicator dynamics. So, this is similar to the Jain-Krishna model, except there's an XIT up front, and that ensures it's always non-negative. In fact, it can, if XIT is 0, it will always be 0, and if XIT is positive, it will always remain positive. It can approach 0 asymptotically. So, this came up in evolutionary biology, and if you sum up the right hand side, it will be 0, which tells you that if you start with a probability vector, that is sum over I of xi0 is 1, then sum of I over I of xit will remain 1 all the time. So, this is a differential equation in the space of probability vectors, and this has been used also. So, it's kind of a reinforcement mechanism. So, Aij xjt is the kind of payoff for species I, that's the interpretation. If it is, and the second term some over jk, xj, xjk, xk, that's the average payoff for the species. So your payoff is higher than that of the species, your fraction increases, that species increases in the number, and if it is lower, it decreases. So this is it was introduced by Taylor and Yonker, and has been extensively studied. In particular, biologists are interested in extinction and non-extinction, so they don't care whether it converges or not. They have been looking for conditions under which it stays away from the boundary of the probability simplex. That none of them approaches zero. That's what their interest is. But one can show that it converges in some special cases. For example, Aij is symmetric, it will. And that's more generally that linear object sum over Aij xj can be replaced by a nonlinear object also. And if so, suppose I call that say I replace sum j Aij xj by some di of j, di of x. If this is of the form some partial derivative of something xi of f, it's called a potential game, and if it's called a potential, then also it converges, and that's important in congestion games which come up in communication networks and transportation networks. So there is also a lot of algorithms built around it. So one can say that inside whatever given any convergent dynamics that you can pull out of anywhere, biology or otherwise, there's a potential algorithm. So this is more exotic. So suppose theta is a zero vector. Now I am genuinely going nonlinear. Suppose f is a map which satisfies that for these two properties. One needs some more technical properties, but these two are kind of crucial. That it maps non-zero, non-negative vectors into strictly positive vectors. That's for strong positivity, and it's positively one homogeneous in the sense that f ax is a f x for a positive. Then there's a generalization nonlinear version of Perron-Frobenius theorem which applies, and it guarantees some clone of unique lambda positive and unique vector x star positive, so that f x star is lambda x star. And that's a nonlinear eigenvalue problem, and there's a version of power method works. So you just keep iterating xn plus 1 is fxn divided by norm of fxn that converges. And this comes up in iterative solutions of dynamic programming equations for when you want to, when you have exponentiated cost, basically, or reward, whatever. So you are getting a reward which is e raised to sum of something I equal to 1, 0 to n, whatever instantaneous reward. And you want typically random, the expected value of that, and you want to see what the asymptotic growth rate is. So you want to, and this is natural in math finance because there is this kind of compounding effect. When you invest x rupees and may want to expect to make profit, you won't make x plus epsilon. You would make x times 1 plus epsilon. This multiplicativity is natural there because each rupee gains by epsilon, say. So 1 rupee goes to 1 plus epsilon, x rupees will not go to x plus n epsilon, but x times 1 plus epsilon. So because of that, this exponentiated cost, how fast it increases, etc. So it leads to, and the nonlinearity comes because of maximization or minimization. You are trying to, it's a control problem. You are trying to maximize or minimize. So that gives the nonlinearity, and because it's a kind of max of or min of some bunch of linear operators, it has those properties, positively one homogeneous, etc. Oh, I did not show it explicitly. I just said that it's nonlinear. The standard example is, the kind of thing I am describing is there is a non-negative matrix indexed by u operating on x, and you have max over x or min over x. So I said I will preach a bit. I have got a few minutes to preach. So this. So I just want to make a distinction. Okay, the distinction is on the next slide. So if you think of classical engineering, which is typically dealt with generation, storage, distribution, and utilization of energy, materials, and gadgets, artifacts, and the mathematics traditionally went with it, which all of us, I don't know whether, syllabus has evolved over the years, so hopefully it has changed. But those who learned from a Bible called Advanced Engineering Mathematics by Krzyzak, it was completely dominated by this. ordinary partial differential equations, numerical analysis, transform method. Of course, there are other things, but they are kind of de-emphasized. And now it's, I mean, it's not that these things are not there, but now they have gained more prominence with generation, storage, and distribution of symbols and basically information, either abstract symbols or some signals. And the mathematics required different, and I have highlighted the main theme of this school, which is linear algebra, particularly the computational linear algebra, and optimization, which is grossly ignored, I think, in the country, and then probability and statistics, algebra, and by modern graph theory, I mean not again, see, I am a kind of academic dinosaur, so books I think of are probably dead and forgotten. So there's this Frank Harari and other such graph theory books, which did some exotic, cute things about graph theory. But I think now what matters now is somewhat different, like spectral theory of graphs and random graphs and so on. And finally, the theory of computation. These are taking the centerpiece basically, and even more recent in some of the more specialized topics you see also in computational topology or differential geometry. So what I feel is that this has to be acknowledged as a separate, not necessarily separate, but a distinct stream of applied mathematics, and emphasized and promoted as such, because applied mathematics somehow always means computational fluid mechanics and computational PD, and somehow that I feel is a myopic view. So JKV is still around. Hand over the message for all the senior mathematicians here. Although you accuse me of being a mathematician, but I'm in E department. I can influence nothing in mathematics. Okay, so let me quickly go through the references. So this is an excellent book actually. This is what I have used. It's maybe a little dated, but it almost reads like a storybook. And they have a later paper which is kind of a little more detailed. Then this is the paper Avrachikov, etc. who analyzed this. Sebastian Vina, this is the Spectral ranking is another core resource for me. It's an excellent survey which was evolving on the unpublished for several years before he published it. Cards, as I said, a historic piece on sociometry. This is another excellent book. This John Kleinberg is kind of one of the patriarchs of this area. This is the author and whatnot, author journal ranking work. Yeah, so this is the eigentrust algorithm for reputation based ranking reputations P2P networks, and this is the Devrat Shah and students rank centrality. Okay, this is like in fact the Jain Krishna model I mentioned. So Sanjay Jain is now in Delhi University. Sandeep Krishna was the student, is now in NCBS in Bangalore. This is the big paper on promoting multiplicative weights, Arora, Hadan, and Kali. The original paper on evolutionary stable strategies. I mean, this came up in game, basically that replicator dynamics had some evolutionary game motivations. And this is the, okay, this is other Kleinberg, they are brothers. This paper show the passage from multiplicative update rule to replicator dynamics. And that's hopefully the end, yeah. Thank you. So I ran through the references very fast, but anybody wants, I can send you the list.